Hello everyone, welcome back to the channel. I hope you guys are doing amazing. Welcome to the eighth video on our DP series, and we are doing DP on grids. I guess this is our third video on this topic, and today we will take up very interesting problem, which is cherry pickup 2. It is not so difficult if you try it on your own, and this has been asked in quite a lot of good companies interviews like Rubric. Let's see the problem. And for this problem, as I had told you, on for DP on grids, first you try to solve it in iterative manner without doing any recursion or memoization. Okay, so you should definitely try this problem on your own first in an iterative version only. But I will show you for this particular problem only. I will show you how we can do recursion to memoization and also to the iterative version, how we can do for DP on grids also. Let's see the what the problem statement says at first. You are given rows comma column matrix grid which represents a field of cherries. Okay, so in each of the cells there are some cherries and it is represented by some numbers. You have two robots. One robot is in the top left corner and another robot is in the top right corner. Okay, so in a n cross n grid, you are given two robots. One it is in the top left and top right. If the grid is bigger, then also it's the same. So uh, in every iteration, so what does the robot do in every iteration? It moves downwards, but within downwards also it has three direction. It can move to the right, left, if possible, or down. So in every place it has three choices. Every robot has three choices to move, and it must pick up all the cherries in its path. And you need to maximize the sum of, I mean, you need to maximize the total number of cherries picked up by both the robots, sum of the total number of cherries. So if you see, this robot follows a path of first downwards, and then it goes to the right, and then it goes to the left, and then it takes a total of 3 plus 2 plus 5 plus 2 number of cherries, which is 12. And for the robot 2, it takes up 1551, that is also 12. So it takes a total of 24 cherries. You can see in this example also, it goes to the right at first, the robot 1. Simultaneously, the robot 2 goes left, and in one place it goes downward, vertically downward, and at the last step, both of them goes to downward but left. Okay, so in the way they carry a total of 28 cherries. They collect a total of 28 cherries, and if they happen to coincide in some cell, then they do not, I mean, they collectively carry that particular cell only. So let's say uh, in this in the from the going from the third row to the fourth row, if robot 2 had jumped from 0 to 5 instead of 0 to 4, it wouldn't have been able to collect these four cherries, and it would not again collect these five cherries because it has already been collected by robot 1. So cumulative of robot 1 and 2, they have only five cherries if they both have moved to the same cell. So you can say that we will prefer not to move in the same cell. Okay, you can tell it like that, that we will prefer not to move in the same cell. Okay, and if you see, the constraint are something like 70 and grid of ij is 100. So that's okay, that's okay. So how can you solve this problem? So first try to do a recursive method. So see, every time you go downwards, and robot 1 has three choices, robot 2 has three choices. If you take a, they are independent choices, right? First of all, they are independent choices. You have a total of nine choices. So why do I say nine choices? Because if a robot 1 moves left, robot 2 can move three direction to the corresponding left, and then again, so I guess you already understood that how this 9 is coming. It's nothing but 3 into 3. If let's say robot 1 goes to left, then in that case robot 2 might have gone to left or right or vertically down also. And in the similarly, when robot 2 is moving to right, again robot 2 has three choices. Robot 1, sorry, this is robot 1 is moving to right. Again it has three choices, and then when it is moving to downwards, then again it has three choices. So that's why I am telling that a cumulative of nine choices you are having. in each of the iterations. Okay. And if you move to the same cell, just take care that you do not collect any extra cherries. So that's all you need to do. And if you just check that every time it is both of the robots are moving simultaneously vertically downwards. So in order to, first of all, what you need to do is find the states of the recursion for which you need to write. So can you tell me how many states do you need to uniquely determine the location of robot 1 and robot 2? Can you tell me this? So, first of all, the robot 1 is present in the top left and robot 2 is in the top right. So, in every iteration, you know that it is moving one step down definitely. Okay. So, in the vertical direction, they are always in the same row. They are always in the same row. So, in the vertical direction, there is need to be an index. Okay. Index I, let's say, which will go till n. Okay. You have this state. And you, for robot 1, let's say you are in some column, right? You are, let's say, in the, you can, for robot 1 you can be, let's say, in the first column or in the second column and so on. So you need another I mean dimension for that. And for robot 2 also, you need, so you get a total of 3 dp states. Okay, 3 dp states. Three recursive states you can call. So initially, what are the initial conditions of the robot? Initially, the robot 1 is in the zeroth column. Okay, initially the robot 1 is in the zeroth column. So if you try to return something, so first of all, if you try to write what is n, is nothing but grid dot size. This is the number of rows actually, and every time it's first of all it starts from 0. Okay, this is nothing but the I state which can go till n, and it starts from 0. So if I try to write some recursive function, calculate, let's say, you pass the grid and you pass 3 indices. Okay, so let's say it needs to be I, R1 and R2. R1 is represented by the column number of robot 1, in which column the robot 1 is there, and R2 is nothing but the column number of robot 2, in which column robot 2 is there. But you see, initially this I is 0. You are starting from the 0th row, and the robot 1 is in the 0th column, and the robot 2 is nothing but the column number last. Column number last is nothing but m. If I write m, then I need to define m also, grid of 0 dot size. It's nothing but grid of 0 dot size. I hope you understand this. I hope you easily understand this. And now you can easily write a recursive function. To this. So let's write it. Let's just write it quickly. If you copy this grid, and what do you have now is something like the index. Okay, it will go from, from 0 to n minus 1. Okay, and you have row 1 or robot 1 and robot 2, the coordinates of both of the robot. Okay, so what do you think you need now? What do you think you need now apart from this grid dot size and this m? Again, I am just doing it. I'm just because we will need m and n anyways. So I'm just doing it. So what do you think will happen if these robots reach to the uh, last row? That is, if it reaches to the last row and it also goes to the next one. Okay, after picking up those cherries from the last rows, if it goes to the next one, it means that if this index goes to something like n, so it means that from 0, it has started from 0, it went till n minus 1, and then it has moved out. Then it cannot collect any more cherries, right? It cannot collect any more cherries, and then in that case, you can simply return 0. You can easily and very simply return 0 in that case. And now, how will you do next? You can do it very simple. Is that every time the index is getting incremented by 1 in every iteration, but you see you have 3 choices. So this column number can be -1, it can be 0, it can be +1. So same for the robot too. So let's say what are the transitions? Always this index will go to index +1 because it is moving to the next row always. R1 can be R1 minus 1, it can be remain R1, it can be remain R1 plus 1. Note that R1 is the column number of robot 1. So it has three choices. Similarly, R2 has same three choices, same choices, right? So what can you do? What can you do? There are a total of 9 choices, as I already told you, right? There are a total of 9 choices. So what you can do now is have something called X. Have something like X, which will go to something like X equals to 0, X less than equals to 1, X plus plus. Okay. And what can you do? You can add this X. You can add this X to this R. Okay, so you can add this X, and let's say also keep a Y, which will get added to, let's say, R2. This Y will also behave the same like X. This Y will also behave the same like X. And what you need to do the transition is you will do R1 plus X, and you will do R2 plus Y. So I hope you understand this. R2 plus X means that one by one we get all the values of -1, 0, and +1, and same for R2. So what do I need to check now? What do I need to check now? Are they within the range? Are they within the limits? Are they within the limits at all? So if R1 plus X is less than 0, uh, not less than 0, is greater than equals to 0, okay, and they must be within, they must be within the limits, right? They must be within the limits. So R1 plus X, are they also less than M? Okay, R1 plus X, are they also less than M? And you check whether robot 2 is also getting, also having some valid coordinates or not. So R2 plus Y, they also need to be greater than 0, and R2 plus Y also needs to be less than M. So these represent that they are still within the grid. You are not moving out of the grid. So you see something like robot 1, if it moves towards left, it is moving out of the grid. So that is something, it's index 0, it's moving to index -1. So that I'm just checking that it should not move something which is outward. It should not move something which is out of the grid, which is something which is out of the grid, right? So if they are lying within the grid, you can choose to move. You can choose to move. So what can you do now? What can you do now? You can collect all the cherries, right? You can choose to collect all the cherries. So what you can do is that you can do something like calc, pass this function, you grid, and index will always go +1. R1 you increment by X, R2 you increment by Y. Okay, I hope you understand this, how this is happening. And this is what? This is returned by, this returns the number of cherries. Okay, so what if you are collecting the cherries which is at present? So you will get something like grid of nothing but grid of, let's say, R1 plus X. So can you tell me how can I do this without uh, doing something like R1 or R2? So can I do something like this? R1 minus 1, it goes from R1 minus 1, it goes from R2 plus 1, or something like R2 minus 1 and R2 plus 1. So if you see why I am doing this, I am iterating from R1 minus 1 to R2 plus 1, and in turn I can only write X. Instead of R1 plus X again and again, I can only write X. I hope you understand this, right? I hope you understand this. So that will be a little bit helpful. It will help to look our code clean. So you will also get something like grid of X, okay, and grid, you are in the, first of all, you are in the index and grid of X, plus you are, if you are picking up both the cherries, it will be something like this. You are in the current index and picking up these cherries, and also going to the further value, but this answer you are doing maximum, right? You want to pick up all, you want to take all of my choices and tell me which is the maximum one. Tell me which is the maximum one. And if you see, you can just move this x and y. So I hope you understood this easily. I hope you easily understand this. But if you can you tell me what if they both land in the same grid? What if they both land in the same grid? If x is equals to y, if they are both columns are coinciding, then you don't need to do all this. You don't need to add it two times. You just add a single time. Okay. So what you do, you just add a single time instead of these two times additions, and you write this in else. Okay. So if they are coinciding, the robots are coinciding, then you add a single time. Otherwise, you add the grid value. You add the grid value of both of the robots. You add the grid value of both of the robots. So I hope you understood this easily, right? uh, Let me have the answer as something 0. Okay. So if you try to return this answer now, uh, what will you get? What will you get? Will you get the correct answer? Did I do everything correct for the recursive solution? What do you think? So let's see. You see, we have the accepted case. If you try to submit it and check, if you try to submit it and check that everything went really well or not. So you see, we are getting a wrong answer. It means that definitely we have committed some error in the solution. If you try to see this x and y, what are these x and y? These are nothing but the future column indices which we want to move to. These are the future column indices which we want to move. Okay, so we don't, so these are the future column indices which we want to move to. Currently, we are in the R1 and R2 only. So we need to check R1 whether R1 is equals to R2 or not, and not x equal to y. And you see here the marking should be taking the current cell. Okay, so taking the current cell should be something like this and this, not x and y. These are the future values which we move to. So we need to write the values which we are moving to in the recursive function, and not the other way around. So I hope you get it easily. Why do I need to place R1 and R2 here? So if I try to run this code now, will it work? Let's check if it now works. You see, we have the accepted thing. If we try to submit this recursive solution, what do you think will be our result? So you see, we get a TLE, which is very much expected because we have not memoized it, or we have not done any iterative or recursive DP for this. So as I had told you, we can do a simple uh, solution. We can do a simple iterative recursive DP. Okay, so we will memorize it. We will memorize it. Okay, so how to do that? How to do that? Uh, so what we can do? I will initialize a DP table, which will be you see the maximum value is 70. So we have three values, right? We have these three. I mean these three rows and columns. So it can be a maximum of 3D. So three dimensions are there. So we will write 71, 71, and 71. Okay. And we will initialize all the values with a -1. So we will do mean set DP -1 size of DP. Okay. So it initializes all the values with -1. And here we will do something like, if we are doing caching, like we are treating it as a cache memory. So I will tell you that if in DP of index and R1, R2, it is not -1. If it is not -1, then do not calculate anything. Do not calculate anything. Just return it. Just return it simply. Okay. And uh, else what you can do, you can just store this value in your DP. You just store this in your cache memory. Okay, so you are just storing this, and that's all you need to do. Let's try to check if this works at all. if this will work completely. This is our memoized solution, and it should give a accepted version. I think it should give a completely accepted if we try to write the submit it, and you see it gives accepted, and also it gives a good runtime complexity. Can we write the iterative version for this? Can we write the iterative version for this? So what do you think? What do you think? Definitely we can. Definitely we can, right? So let me initialize the DP now by something like DPIJK. Okay, so we will have DPIJK, no problem with those. And you see, we need to write the base case first, right? So index, if index is n, we will return 0. So let us have IJK, 3 dimension of DP, and the first dimension is nothing but n. So we will move through all the j and k. Okay, we will move through all the j, and we will also move through all the k, and tell that if this I value becomes n anywhere, so if this dp of njk, always initialize it to 0. Okay, I hope you easily understood this. This is nothing but the base case which I am writing. I am now converting my recursive dp to iterative dp. So I have written my simple base case here, and now I will just do I from I. This is a bottom of dp, so I will try to move it from backwards. uh, so this is nothing but this. I hope you get this. I hope you get this easily. There should not be much doubt about it. There should not be much doubt about it. Okay. So, what if you go from, let's say, n minus 1 to 0? You need to calculate this value, right? So, what do you get now? What do you get now about this I? About this I, we have this n, and let me do something like this also. J minus minus. We are iterating through all the values. So I will do something like this for every one of them. Okay. I will do something like this for every one of them. And what we do in these is just copy the code. Okay. So if we try to copy the code here, will it work? Let's see. Let's check it out. We have an answer, and what are our values? This I represents nothing but our index. This j represents nothing but our r1. This k represents nothing but our r2. So we need to replace each and every of them, right? So all the r1s we need to replace it by j. So let's do it quickly. Wherever you see an r1, just replace it by j. Okay. And wherever you see this calc, you just replace it by dp. Again, for this, do the same thing. Just these are just manual things, right? I hope you can easily get this. There is not much difficulty in these things. If you have been following my playlist from the starting video, I think this should be very trivial to do. Still, I am showing it for you. I am showing it for you. So I converted all the R1 to J. I need to convert all the R2 to K. Okay. So let me have it. Let me have all the R2 to K. Okay. This is nothing but K. And this R2 is also nothing but K. Then I need to convert all the indices I and D to I. So let's convert these to I. I hope you understand what I am doing exactly. That's how we usually convert our recursive solution to an iterative one. I just copy the code and I just simply write I just simply change the variables, and I save this in the DP also. So what I do is very simple, very easy. I just save this in the DP also and change it to the corresponding values again. And instead of this calc, again I will do return DP. It will be very simple. It will be nothing but like this, 0, 0 and n minus 1. Okay, so if we try to run the code now, definitely we won't require this whole thing. Okay, definitely we don't need this whole thing right now. So if you see and check what is the thing going on now. So if we try to submit it and check if it works. So let's see. We do get a wrong answer for this. We do get a wrong answer for this. Can you tell me what's the error in the code? So you see, what the error is that this n needs to be m, right? Because this index goes from 0 to n. So this index can go from 0 to n minus 1, which is along all the rows. But these R1 and R2 goes to 0 to m minus 1, not n, right? The dimension is m minus 1, as we had already calculated here m. So I need to change these n's to m. First thing is this. And the mem set dp will not be minus 1 here, right? It will be 0, because I mean, minus 1 was there when we are trying to catch the values. But if we do negative values, if we initialize by negative values everywhere, then it might be a problem, right? Then it might be a problem because we are using some DPI plus 1, something like that. And it needs to be 0, because we have picked, if we have not picked up any of the cherries, it doesn't mean that we have picked up some negative cherries, right? We have picked up 0 cherries exactly. So it's always safe to make this DP 0 now. And now if we try to submit this, you will find that it gives an accepted. So you see, the runtime complexity may not be that much good as much as the memoized version of the code, but many times it varies. Definitely the memory is very good because you are not using an extra stack memory, extra recursion overhead. You are not doing this at all. Okay, so these are the things which matter, because the interviewer may ask you to write the whole iterative version of the DP instead of the memoized solution. But in the competitive coding or in the online test, you can just go ahead with this memoized version of the code also. But since this is a DP on a grid, I will suggest you to write this iterative version directly. I hope you can do it. Okay, I hope you can do it, because once you get to know you need 3 indices and what those indices, those states of the DP represent, it is quite easy to visualize that what are the possible choices that you need to do. And you see, somehow this runtime complexity, as I ran it again, I just moved this global variable DP to this local variable. It changed the runtime complexity to a great extent. So yeah, that's all I guess. It was a hard problem of DP on grid. I hope we may do 1 or 2 more questions of DP on grids, and then we will move to the next topic. Thank you so much.